in the past, you have heard many wonderful applications of the trace formula. Today, we'll be looking into the trace formula. So the first talk today is given by Pierre-Henri Chaudouard. Okay, so the first speaker today is Pierre-Henri Chaudouard, and he will talk about on the Guo-Jacquet trace formula. So please.
Thank you. So I would like first to thank the organizer for the invitation. It's an honor and also a great pleasure to be here. I should say that the first paper I had to read as a PhD student was a trace formula for reductive group 1 by Jim. And so the papers by James were and are still a great source of inspiration for all my research. And even my the part of my research that had to do with algebraic geometry, and I think this will be also true for the talk today. So I would like to speak about an ongoing joint project with Guo-Jacquet. And first, I would like to give some motivation for this work. So I fix an integer n, a number field f, and A will be the ring of adels of f. And I will consider a central division algebra over F. And I will consider the algebraic group G, which is GLN of D. So I always fix a central group in GA. More precisely in G F times R. So in the product of Archimedean places of R of F. So this is a central subgroup. It is in fact isomorphic to R star plus. And the fact is that with such a subgroup, J mod GF divided by 8 infinity is a finite volume. Okay, let me also fix a pair of integers, P and Q, such that P plus Q is N, and we'll consider a subgroup of G, which is a product of GLP of G times GLQ of this. It's a subgroup, a Levy of G. And I will denote by H, so bracket H. So this is the usual automorphic quotient, HA mod the rational point, but I will put also a sub G, which means that I also divide by the subgroup AG infinity. This is not a finite volume. I also fix an invariant measure on bracket H. And I am interested in psi pi, an automorphic representation of GA. So loosely speaking, it will be a constituent, maybe of the L2 space of G. Maybe it appears in the continuous spectrum. But I will assume that the central character, this is irreducible automorphic representation, central character of pi is trivial on the central subgroup H infinity. Okay, so now let me give a definition. We will say that pi is H distinguished if the following linear form, I call it H period. So this is a linear form denoted by PH. It is on the space of pi. And it is given by integration over H bracket G. Okay, so remark if pi is cuspidal, so to integrate phi. So if pi is cuspidal, then phi is rapidly decreasing on H bracket G. And in this way, the integral is convergent. So if not, so the integral may diverge. For example, you can take the constant function, and the bracket H sub G is not a finite volume. So we have to consider some regularization. If we want to have a well-defined H period. And the following question is of central interest for the talks is what is the H distinguished part of the spectrum, the automorphic spectrum of G? Sorry. Okay, so if I do not put if the H period is not 0. It's okay? This was the missing part. Thank you. Okay, so you have this this integral over the space of pi, and if this linear form is not identically 0, then we say that the representation is H distinguished, and the question is, can we characterize this part of the spectrum of G, the automorphic spectrum, which is as H distinguished? So this is, in some sense, what is the automorphic spectrum of G mod H, in some sense. So the symmetric, so this is a symmetric space, and so nowadays, so this is a question that belongs to the realm of the relative Langlands program. Sometimes to understand the automorphic spectrum of symmetric varieties and more general spherical varieties, as emphasized by Sakellarides and then Kattesh. So let me give some results about these questions. So I have to put some restriction. So I will take first this simply F, and I will also assume that P is equal Q, so that N is 2P. And this question has been studied by several people, but I want to mention a theorem due to Friedberg and Jacquet. There are also related results due to Bump and Friedberg, and also Jacquet, Shalaika, and so on. So, so let pi be a cuspidal representation of G. Then pi is H distinguished if and only if, so pi is of symplectic type. So we already encountered such a definition. So this means that exterior squaral function of L has a pole at S equal 1, but equivalently by Jim's work, This means that pi comes from an orthogonal group, SO2n+1. And this also means that the long length parameter factorizes through sp2n. So this is why it's called symplectic. It's a symplectic type. And moreover, the standard L function of pi at 1/2 does not vanish. Okay, so we have also a result about the discrete spectrum. So we know precisely what part of the discrete spectrum of G is H distinguished. So this is due to Chang-Yang. We can look also also at the case where P is not Q, but still D is F. No. So we have we can describe exactly the part. So you have the Meuglen-Vaspurger description of the discrete spectrum, and in terms of the cuspidal representation you induced, you have a characterization. So in particular, you have to induce from a cuspidal representation of some GL R with even R, for example. Okay. So in this case, so by Friedberg and Jacquet, there is no H distinguished cuspidal representation. Okay, so maybe you are slightly disappointed, but it's life. But nonetheless, they studied an interesting case. So if Q is P+1, then you can produce not a cuspidal one, but close to cuspidal representation that is H distinguished, or at least in some cases. So we look at the induced representation from a parabolic subgroup of, so here we are with GL2P+1. So we are induced from the parabolic 1 to P. Okay, so we look at such an induced representation where pi is cuspidal. Then such representation is H distinguished if and only if pi is of symplectic type. Okay, so we do not have this further condition. In fact, we have a shift in the period. So the condition is automatically. So we have this kind of condition, but it is automatically verified. Yes, D equal to F. So we have the trivial representation of GL1, a cuspidal automorphic representation of GL2P. If it is of symplectic type, that this representation is distinguished. Okay, so what about the initial problem about central divisional algebra? So the method for GLN are based on some integral representation of some zeta integrals that are related to L functions. And in general, we do not have such things for division algebra. And so maybe we have something else to do. And we can states the following question. So let pi the automorphic representation of GLN G. We can consider is Guo-Jacquet transfer established by Badulescu and Renard in general. So this is a representation, an automorphic representation of GL and D of F. So D square, D to the square is the dimension of G. And is pi GLN, so GLP cross GLQ of D distinguished, equivalent to the fact that the Guo-Jacquet transfer of pi is GLP times D times GLQ times D F distinguished. That is a distinction property is preserved by the Guo-Jacquet correspondence. So it is conjecture to be true, at least if pi is the cuspidal and the Guo-Jacquet of pi is also cuspidal by Chang. So P is Q, conjecture. And I have also to mention a conjecture of Guo and Jacquet, a twisted variant of this. Conjecture Guo-Jacquet. So now we suppose that D is a quaternion algebra, may be split, which contain a quadratic extension. So associated to the quadratic extension E, I have a quadratic character of the adults. And the conjecture is the following. So let pi be a cuspidal automorphic representation of GL and G. Then pi is GL and E distinguished. So this is the same definition. I have to replace my group H by GL and E. Is GL and E distinguished? Then it implies that the Guo-Jacquet transfer, which is a so we assume that the Guo-Jacquet transfer is cuspidal. So such that cuspidal is a cuspidal augmentation of GLN, GL2N. Then the GLN pi, so the Guo-Jacquet transfer of pi is GLN cross GLN distinguished, and also it's twist by eta composed with the determinant. We have the two conditions. And in fact, for the n equals to 1, this is a theorem proved by Valls-Purget and reproved also by Jacquet. So Jacquet uses a different method. He introduced a relative trace formula to reprove Valls-Purget results. And with Guo, they suggest an approach via a relative trace formula. So the paradigm is that we expect a relation between distinctions and Guo-Jacquet transfer, and more precisely, we can expect an analog of the endoscopic character relation. That is, we expect some relative character relations between the representation pi of GL and G and the representation of its the representation that is given by the Guo-Jacquet transfer of pi. And this relation should be in a dual of relations between orbital integral. So these conjectures motivate the construction of a relative trace formula for example, the H period. And this is precisely the first part of our project with Guo-Jacquet. So of course, in the literature, we can find a simple relative trace formula. And for example, there are results due to Fagon, Martin, and the Whitehouse, which prove some cases of this conjecture using the simple relative trace formula. But when you use simple relative trace formula, we have to put some restrictive condition, some restrictive local condition on pi. So you cannot get the full statement. So our goal with Guo-Jacquet was to establish a full relative trace formula. So now I would like to explain to you our construction. And this is, I take the opportunity to review some works of Jim. So let me give the basic constructions. So I will focus just on the case where G is F, just for simplicity. So G is simply GLN. So when I start from a Schwarz function G of A, so Schwarz function means this is a smooth function, and all the derivatives are rapidly decreasing. So this includes the space of smooth and compactly supported function on GA. So we can attach the automorphic kernel. So this is the automorphic kernel, and basically the trace formula consists in so I have still P plus Q is N, and the group H is GLP plus GLQ. And the problem is to integrate K over H on the two variables X and Y. So first I can integrate the bracket H, K, X, Y, dy. So in the Y variable, the kernel is rapidly decreasing. You can integrate this. There is no problem. But now the function we get here is only of uniform moderate growth, and it is not rapidly decreasing. And you cannot integrate directly over H. Well, I have to caution by the central group I mentioned at the beginning of the talk. So we would like to perform such an integration. So because formally this gives you an expansion of the kernels in terms of the periods, or rather the relative character attached to the H periods. But we cannot do this, and so we have to appeal to Jim's methods to produce a modified version of the kernel so that it is integrable. And okay. So let me review now some of Jim's method. So all the construction depends on the choice of a maximal compact subgroup. I take the standard one, standard maximal compact subgroup of GA. And we have, so for any parabolic subgroup, we have function HP from GA to the dual space, the real dual of the character of the parabolic P. So this is given by, so when you evaluated HP of G, say of P of K, against the character, this is the log of the product of the absolute value of P, and what is P in K. K is chosen in K, and P is chosen in P of A. And by Weatherwaite decomposition, any element in GA can be written as a product of an element of P and an element of K. Okay, so we have such a function. And inside the AP, we have some open cones. One which is acute, the other one is obtuse. So the first one, the acute one, is dual to the simple root, and the obtuse one is dual to the weight. The weight is the roots. So we have the P0, which is the usual Borel. So in AP0, so for GL3, so we have here AP0 plus, and we have here AP0 plus on the right. Okay, so we have such open cones, and I use characteristic function of such cone, which are denoted respectively by tau p and tau p hat. Okay. And I also fix a parameter T, which is in the closure on the acute veil chamber associated to P0. And then associated to this thing, so essentially the maximal compact subgroup of GI and the parameter T, we have a canonical partition. Canonical partition of GI. So for any G in GI, when I sum I have such a sum, I will explain it. So T gives you by projection parameter TP in AP plus. So this tau p is the characteristic function of the acute veil chamber. I'm summing over pair P delta. So where P is a standard parabolic subgroup, so P contains P0, and delta belongs to GF mod PF. So basically, so we are describing all the parabolic subgroup of G defined over F. And this function is a characteristic function of a compact subset of GA. So it is invariant by K. So the quotient. So we take the quotient GA, and on the left by, so I write P in Mn divided by AM infinity. So the same group, but for the Levy M as before, MF and A. So this is the first things that James notices. A second tool he introduces is a truncation operator. So we start from phi, a function on bracket G, and you define lambda t of phi as the sum over the same pairs of, so we have a sign, minus dimension of LP minus dimension of XG of, so here we use the characteristic function of the obtuse chambers, so P HP delta G minus T, phi P delta G, and phi P is a constant term. Okay, so I forgot to mention that where P is G, the two functions are just one, identically one. And what is the property of this truncation operator? Then it transforms function of uniform moderate growth on G into rapidly decreasing function on G. So for example, you can apply this truncation operator on the left variable of K, and you get a function of two variables that is rapidly decreasing in two variables, and so you can integrate. So this is the first construction of the trace formula, but this construction is well suited for the spectral expansion. But so we have still to introduce a modified kernel to get a nice geometric expansion. So now I want to give you a relative version of these two constructions. So now I assume that G is in HA. So H can be seen as a group fixed by the automorphism theta, which is given by conjugation by the following matrices: identity P minus identity Q. So now G is fixed by theta. And so because the partition is canonical, then P delta has to be theta fixed. And theta fixed, this means that we can replace the pair P delta by pair P W delta, where now W is an element in the Weil group attached to the diagonal torus. So this is the Weil group. What VP and delta. Now delta is in HF, and moreover, so such that PW. So when I conjugate P by W, I get now a parabolic subgroup that is not anymore standard. It is just semi-standard, but I want that it is relatively standard. That is, the intersection with H contains P0 intersected with H. It is relatively standard. Okay, so the upshot here is that in general, we have to sum over all the parabolic subgroups. But for the relative partition, we take the same terms, but we sum over just parabolics, which are relatively standard. Okay? And we have also a relative truncation operator. So I have to put, so if I sum over PW delta, so the translation is that, so c'est delta prime. The translation is that you send W delta prime to delta prime. So we have to replace all the delta W delta prime. Okay, so we can do the same game here. And you get the relative truncation operator, and now it transforms function of uniform moderate growth on G into a rapidly decreasing function, not on G, but on H. But since we want to integrate over H, this is good for us. So we can still use this mixed truncation operator. So this idea to use a version of Arthur's truncation operator are due to Guo-Jacquet, Lapide, and Rogaski. So why do we use such modified truncation operator? This is because the less you truncate, the easier are the computation. So in general, it is difficult to compute the truncated things. And in the same spirit, we can introduce now the modified kernel. It depends on the parameter t. X and y are in the subgroup H of A. And this is given as a sum reminiscent from the truncation operator. So we have a sign. There is a condition. So we take the characteristic function of the obtuse wave chamber. And we have also to sum over the other variable. So we take the same P, but we complete P by another triple. And we use another kernel, W delta G X, W prime delta prime Y. So what is KP? So we have the space, the L2 space associated to GA mod. So I write P as a product of the Levy unipotent radical. So I'm looking at the L2 function on GA that are invariant by MF and NA. And the test function F acts on L2, and this gives you a kernel KP. And this can be written as a sum over the rational point of the Levy and an integral over the unipotent radical. Okay, so this is a modified kernel. And this modified kernel has two expansions. So we have two expansions. So one which reflects the decomposition, the long-length decomposition, the coarse long-length decomposition of L2P according cuspidal data, that is a pair of Levy and the cuspidal representation, mod sum equivalence relation. These are cuspidal And so the kernel Kp is the sum over all cuspidal data of kernel Kp chi. And we have a geometric, so this is a spectral expansion. We have the geometric expansion. You can use the map from G to its categorical quotient by the action of H cross H. That is, we are looking at the space of function on G, which are left and right invariant by G. In fact, this is an affine space of dimensions minimal of P and Q. So let me denote this quotient by C. And if I have a rational element in CF, so let me denote this map, this canonical map by A. So I will take the O part of Kp simply by asking that gamma is such that it's invariant, its image in the categorical quotient is precisely O. So we have also Kp is a sum over all rational elements in the quotient of Kpo. So now, we have some, I can put a star here. So I will define Kt star as a sum, as the alternate sum of the Kp star, where star is either a cuspidal datum or an element in CF. Okay, so in this way, you see that the modified kernel is either the sum over the modified kernel attached to any element in the categorical quotient, or the sum over all modified kernel attached to cuspidal data. So now I can give you a first theorem. So this is a convergence theorem. So it says that when you sum over all the cuspidal data, you can, of the integral over the modified kernel, over the product of bracket H, of the absolute value of the modified kernel attached to K, then it is finite. And you have the same statement for the geometric expansion. When we sum over all the rational points in the categorical quotient of the integral of the absolute value of the modified kernel, then it is finite. And moreover, we can compare the modified kernel attached to a cuspidal datum with the kernel where we apply the mixed truncation operator. So for any positive R, the sum over all cuspidal data of the integral over H of the difference between, so I applied the modified truncation operator on the left variable minus the modified kernel, then it is less than an exponential, a decreasing exponential. And for all t, say sufficiently positive, sufficiently deep in the chamber. Okay, so we have strong analogs of Jim's result in our relative situation. And this enables to define distributions. So for cuspidal data or an invariant, we can define a distribution by integrating the corresponding modified kernel like this. So a priori, this depends on T. And this is an exponential polynomial in T. And we define our final distribution as a constant term. Okay, so a priori, this depends on the parameter, but the dependence can be explicitly as a polynomial exponential in the variable T. And so we can define a constant term, and this is my final distribution. So we get an identity like this. We sum over all key data, cuspidal data, and which is equal to a geometric expansion, which is a sum over all the rational element in the quotient of GO of F. So this is the coarse form of the Guo-Jacquet, the trace formula that Jacquet-Guo suggested for linear periods. Okay, so now this is just a first step, and we would like to understand more precisely what are the distributions, and we want to have more explicit expression about these distributions. So let me give you some computations. So some geometric computation first. So let me assume that P is less or equal than Q. So remember that we have this categorical quotient. So this factorizes through G mod H. And G mod H can be identified by G maps to G theta G inverse. So remember that theta is involution given by the inner automorphism given by conjugation by identity P minus identity Q. And this is a set of G in G such that G IP I minus IQ is conjugate, is G conjugate to IP minus IQ. And so we can factorize the categorical quotient by a direct map from S to C. So we have a second action of H on G by left translation, and this gives you an action on H on S by conjugation. And now S is also C is also the categorical quotient of the action of H by conjugation. And so now we have a simple description of this map. So any element in S can be written as a matrix by blocks, A, B, C, D. And the map, in simply, you associate to this matrix the characteristic polynomial of A. Okay, so this gives you the categorical quotient. And I will give you a description of the distribution GO of F for O in some open subset of the categorical quotient. So the subset is a regular, the so-called regular semi-simple subset. This corresponds to, so C now is identified with the space of characteristic polynomials of degree P. So this is identified with the pi-dimensional affine space. And the regular semi-simple locus correspond to polynomial P such that the discriminant not 0, and also polynomials that do not vanish at 1 or minus 1. Okay, and for such element in this open subset, we can describe the fiber, so 18 minus 1 of O, is in fact simply a GF, sorry, not a GF, an HF orbit in SF. Okay, and more precisely, this is the HF orbit of the following element, can be written as, say, x minus IP, x plus identity P, x, and you add the identity of Q minus P, and the x, which is a condition of x, that's the characteristic polynomial of x has to be O. Okay, so for such element in this open subset, the fibers are simply just H orbits. Okay. So I fix O, and I fix X as before. I have also the centralizer of X in H, and I have AX, which is a maximal split central torus in HX, and I can look at the centralizer of this split torus in G. So this is a Levy. This is a Levy of G. So now I can state the result. The distribution associated to the test function f and the invariant O is given by some volume attached to the centralizer. So this quotient has to be divided by the same central subgroup, but here attached to the Levy, I am infinity. So this is finite, the volume is finite, times an old friend of Jean. That is, so we have an orbital integral. So for the action of H on S, that apply to another function phi. So H minus 1 X H times a weight Vm H GH. So this is a weight. So I have to explain what is phi. So phi is a test function on S, a Schwarz test function on S, given by essentially integration of F over the fibers. And what is a weight? This is the usual Arthur's weight. That appears perhaps in your 76 papers about characters of discrete series as orbital integrals. So this is the usual weight on the group. So this function is a function on GA, which is right invariant by EK, and which is also left invariant by MA. But the centralizer of X is included in MA. So the integral makes sense. The function VMH is indeed invariant on the left by HXA. So the weight depends on the choice of a measure on IM infinity, but we have the same measure here. So there is a compensation. And also here, the orbital integral depends on the choice of a measure of the centralizer, but we have the same measure here. Okay. And in general, we have so for non-regular semi-simple orbits, we have a kind of Jordan decomposition, and everything reduces to the case of the central invariant, that is invariant associated to the identity element, but eventually associated to other symmetric spaces associated to the centralizer of the semi-simple part. Okay, so I can just say some words about spectral expansions, spectral computations. So for the spectral computations, so we have a few results for the moment. So we have the easy case where the cuspidal data is associated to the group itself. And we get an expression as a relative character. That is an expression that makes appear the H period we saw at the beginning of the talk. So of course, this is 0 if P is not equal to Q, because the cuspidal spectrum is not as distinguished if P is not equal to Q. And for the representation of Friedberg and Jacquet I mentioned, so the induced representation of 1, then the cuspidal representation of GL2P. So this is the case of GLN 2P plus 1. So for such a Levy, so GL1 cross GL2P. Sorry. This is not exactly up. So we have such a representation. So this appears with the cuspidal datum associated to GL1 cross GL2P. So this is inside GL2P plus 1. And this is associated to the cuspidal representation 1 trivial times P. That what you get is in fact, so such representation appears continuously in the spectral decomposition of the kernel, but in the relative choice formula, it appears discretely, but it appears as, let me write up. So what we get is a weighted relative character. Once again, the weighted characters are all friends of Jim. So this means that it is constructed from derivatives of some intertwining operator. So we can switch the two components. This gives you an intertwining operator. And so I have also to say what is pH. So we are in the case where the H period of the Asenson series does not converge, but Jacquet and Friedberg gives you a regularization for such period, and this is the regularized H period. So thank you.